Hey, welcome! Today we're going to pull back the curtain on a really clever data structure. It's something that powers some of the biggest apps you use every single day, probably without you even realizing it.
So let's just kick things off with a problem. Imagine you're building the next big thing, a new social network. A user wants to sign up. How in the world do you check if their dream username is available, out of hundreds of millions of accounts, without making them sit there and wait? I mean, this is a challenge that giants like Gmail and Twitter have to solve literally thousands of times every second.
And this seemingly simple check is what we call the billion-user problem. It's a massive, massive engineering hurdle when you start operating at the scale of the internet.
Look, even for a platform with, say, a pretty modest 20 million users, every single time a user just types a character into that username box, it could trigger a search across all 20 million records. That is a potentially slow, and you better believe, incredibly expensive database operation.
And you know what? It gets worse. Just think about your own experience signing up for stuff. You try Alex, taken. You try Alex underscore, also taken. Finally, you try Alex underscore G underscore 123 and success. See, on average, a user tries 2 or 3 names, which means we're multiplying that heavy database load for every single person who wants to sign up.
So, what are the obvious solutions here? Let's take a look at why the simple, straightforward fixes just completely fall apart at this kind of scale.
You basically have 2 main options. First, you could just hammer the database with a query every single time. As we just saw, this is accurate, sure, but it's way too slow and it just beats up your most critical resource. Okay, option 2, you could load every single username into a super fast in-memory hash map. Now this gives you practically instant lookups, which is awesome for speed, but it's a total memory nightmare. You're essentially creating a full copy of your user list in really expensive RAM, and that is just not efficient at all.
And this is where the hero of our story makes its entrance. We need something that's both fast and space efficient, and that something is the Bloom filter. It offers a truly brilliant trade-off.
So what is this thing? Well, a Bloom filter is a space-efficient, probabilistic data structure. Let's break that down, right? Space-efficient means it uses a tiny, tiny amount of memory. But the real keyword here is probabilistic. It means the filter isn't always 100% certain. And that's actually a good thing.
And that right there is the genius of it. It trades a tiny, totally acceptable amount of certainty for a massive win in speed and memory. It's a classic engineering trade-off, you know? You give a little to get a lot. And what you gain here is almost always worth what you give up.
Okay, let's pop the hood and see how a Bloom filter actually works. It's surprisingly simple, really. It just involves 2 core things, a bit array and a few hash functions.
All right, so picture a long strip of bits, just a bunch of zeros in a row. This is our bit array. Now, when we want to add an item, like the username cat, we run it through several different hash functions. For this example, let's just say we use 2. The first one spits out the number 2, and the second gives us 6. So we just go to our bit array and we flip the bits at positions 2 and 6 to 1. That's it, seriously. Cat is now considered in the filter.
Now let's add dog. We do the exact same thing. We pass dog through our hash functions, and they give us back 2 new numbers, let's say 4 and 10. So we go back to that same bit array and flip the bits at positions 4 and 10 to 1. The state of our filter is now this combination of the hashes for both cat and dog.
And now for the magic. The most interesting part of a Bloom filter is its supposed flaw, which, as you're about to see, is actually its greatest feature.
Okay, so remember, so far, we've only added cat and dog. Now, let's see what happens when we check for a username we know we never put in the filter. Let's check for hen.
So we pass hen through our 2 hash functions, and just by pure random chance, the first hash function returns the number 2, and the second one returns 10. The filter then checks the bit array at those spots. It asks, is the bit at position 2 a 1? Yep, cat set that one. Okay, is the bit at position 10 a 1? Yep, dog set that one.
So, because all the bits it checked were 1, the filter reports back, yes, hen is in the set. But wait a minute, we know for a fact we never added it. This right here is called a false positive. The filter gave a positive result that was, well, false, all because of a random hash collision.
So this is the most crucial point. You have to get this. A Bloom filter never gives a simple yes or no. Its answers are definitely no or maybe yes.
Think about it. If it checks the bits and even just one of them is a 0, it knows with 100% certainty that the item was never added. That's a definitely no. But if all the bits are 1, it can only say maybe yes, because hey, it could be a false positive.
So let's move on and see how this wonderfully imperfect, this good enough data structure is the unsung hero behind so much of the technology you use every single day.
And this is where their power just becomes so obvious. Google Chrome uses them to check for malicious URLs, so you don't have to download a giant list of bad websites. Recommendation engines like Medium or Instagram use them to quickly ask, hey, has this user already seen this piece of content? And massive databases like Cassandra and RocksDB use them to avoid super slow disk reads for data that they know isn't there. Now, what's really wild is the sheer scale of the memory savings. To store 1 million IP addresses the old-fashioned way, you might need around 320 bits for each one. A Bloom filter? With a tiny 0.01% error rate, it needs just over 19 bits per address. That is a reduction of over 90%. It's just insanely efficient.
So the ultimate benefit is actually really simple. The Bloom filter acts like a fast, cheap gatekeeper. It's there to protect the slower, more expensive systems, like a database or a hard disk. Because its definitely no is 100% accurate, it can confidently tell the system, hey, don't even bother looking for this thing, I guarantee it's not here. And that saves a massive amount of unnecessary work.
And that kind of leaves us with a final thought, doesn't it? The Bloom filter teaches us this really powerful lesson about trade-offs. It shows that sometimes being probably right and incredibly fast is way more valuable than being perfectly right but painfully slow. So my question to you is, where else in your life is that true? Thanks for joining me.